For those of you who have taken steel design, you must remember that at maybe the end or maybe somewhere in steel design, there's a place where you can calculate what they call buckling load, right? And I believe that you are provided with an equation, or not equation, many equations to calculate this buckling load. And the buckling load is usually denoted by PCR, and the PCR means critical load, right? You probably still remember that. And this course, the whole idea in the structural stability is to calculate the PCR through structural analysis for different kinds of structures, for columns, for walls, for frames, for beams, for beam columns, for tubes, for arches, for frames. So you will see me solving the problems, looking for the critical load for all kinds of structures. That's the sole purpose in structural stability. Therefore, from this class, you will learn how to use the technique to determine the critical load for all different kinds of elements. Now, before I start that, I will have to start with the bigger picture, which is structural failures. And let me use my note to explain to you what do I mean by structural failures. First of all, let's understand that structural failure is caused by two main sources. The first one is what we call materials failures. And the second one is what we call geometric failures, or failures due to geometry. Now, from engineering materials labs or from strengths of materials, you must have known the following, which is materials failures. You remember that when structures fail or materials fail, there are different kinds of modes. You have learned there's a ductile failures, right? Or ductile materials fails in the ductile mode. Or in other words, when you see the material failing in a ductile mode, you call it ductile material. When you see the material fails in brittle mode, you call it brittle materials. The two most popular examples we have learned so far. One for ductile material is steel. And for steel, materials, you can call it ductile failure or ductile material. How do we define this? Well, we define this as a ductile material because in the stress strain domain, the x-axis being strain is usually denoted by epsilon. And the y-axis is usually denoted by stress. Stress is denoted by symbol sigma. You must know that, right? Even after summer, you still should remember this. What's a typical ductile failure? Ductile failure means this. When you start increasing the stress level, the material will deform. And that means you're going to start increasing this kind of slope. Initially, there is a linear range. And after that, there's going to be what we call the yielding, the formation of yielding. After the formation of yielding, the material will continue expand. And then to some point, it will start increasing and ultimately fail. Of course, there's also another possibility that after the yielding, the materials can also go to downward, which is something like this, and then fail. If after yielding, the material actually will increase the stress level, and that is what we call strain hardening, as you still remember from strength of materials or from engineering materials lab. So the upper curve here is what we call strain hardening. And the other one, of course, is called strain softening. In the end, if you define this, the maximum strain, you can call it epsilon maximum, which is the strain when the material fails. And you can also define another point, which is what we call yield strain, usually denoted by epsilon y. Now the corresponding stress is what we call yielding stress or yield stress, sigma y. And the maximum stress in this curve is the maximum value of this curve is not the maximum strain, but is somewhere here. This corresponds to what we call maximum stress, epsilon maximum. Like this. So what is a ductile material? Ductile material is defined by this, what we call this ratio, and that's called ductility. Ductility is defined differently. In this case, we will use the ratio between the maximum strain and the yield strain. And ductility is usually denoted by the symbol mu. So symbol mu equals the ratio between epsilon maximum and epsilon y. This is ductility. For ductile materials, this value is usually much greater than 1. If that's the case, we call this material ductile material. And of course, the favorite example for this is of we know what structural steels, right? Next one is we call brittle materials. Or brittle failure. Following the same definition, I will not have to repeat because I already say that already. You will know that for brittle materials, on the stress and strain axis, the x-axis is your epsilon strain, y-axis is your stress. The failure curve for a brittle material like concrete usually looks like this. Goes up, and after passing the maximum stress, it will just fail. So similarly, you can also define epsilon maximum here, and also epsilon the sigma maximum, that is the maximum stress. And the yield stress, of course, they're still yielding. But after yielding, there's not much strain that this material can exhibit. Therefore, the yield strain is somewhere very close to here, which is here. There will still be yield strain, except it's very, very close to the maximum strain.
Professor, could you move the screen up a little bit? Yeah, that's better.
Thank you very much. So let me just clean it up a little bit. This is epsilon y. Now for brittle materials, this ratio, mu, will be just slightly greater than 1. But it's not going to be much greater than 1. So this is what we know. Now let me add to the second page. Bear with me with my writing because I'm still learning this technology. Okay, now we learned that how materials fail. And let's look at how structures fail. Suppose I have a column. This will be the first example. So let's call this example 1.